A black hole reshapes our fundamental understanding of reality by turning the universe into a geometric puzzle where space and time switch places. According to Einstein's theory of general relativity, space and time are woven into a single, four-dimensional fabric. Massive objects like stars create dents in this fabric, which we experience as gravity. When a truly massive star dies, it collapses under its own weight into a point so small and dense that it punches a bottomless hole right through this cosmic fabric. This extreme warp means that a black hole is not a solid object or a dark planet floating in space, but rather a permanent dent in the universe from which nothing can climb out. The edge of this bottomless dent is an invisible, mathematical boundary called the event horizon. It acts as a point of no return because the gravity past this threshold is so strong that the speed needed to escape it is greater than the speed of light. Since nothing in the universe can travel faster than light, any object or particle that crosses this line is permanently cut off from our world. Once inside, space itself cascades inward toward the center faster than light can move outward. This completely flips reality. Moving outward becomes just as physically impossible as trying to travel backward into yesterday. Every single path inside the horizon leads inevitably to the center, where all the matter is crushed into an infinitely small, infinitely dense point called a singularity, a place where our current laws of physics stop working entirely. Because gravity warps time alongside space, a black hole acts as a natural time machine that runs at a different pace than the rest of the universe. The closer you get to a black hole, the slower time ticks for you relative to someone far away. If you hovered just outside the edge of a giant black hole for what felt like a few hours, you would look out at the rest of the universe and watch stars explode and entire empires rise and fall in fast forward. Meanwhile, a distant friend watching you through a telescope would see your movements slow down to a standstill as you approach the edge. The light bouncing off you would stretch out until you appeared frozen in place like a faint ghost, eventually fading into total darkness, because the light from your actual crossing could never escape to reach their eyes. Getting too close also triggers a bizarre structural stretching caused by the rapidly changing strength of gravity. If you fell into a smaller black hole feet first, the gravitational pull on your toes would be thousands of times stronger than the pull on your head. This extreme difference would pull your body vertically while crushing you sideways, stretching you out into a long, thin string of atoms, in a process physicists call spaghettification. Surprisingly, if you fell into a supermassive black hole, the boundary is so massive that this stretching force is gentle enough for you to cross safely. You would slip past the event horizon completely intact, floating in total silence while watching the light of the outside universe compress into a small, brilliant ring above you just before you met the center.